Cool. So, I would like to get your feedback when doing these questions. This first one is the synthesis. And I want you to, try to observe what's happening. Try to understand what questions you should be asking yourself, especially when it comes to synthesis and mechanism. Think about what's going on, what do we need to do, what are we using, and what reactions you've learned so far that will allow you to do such a thing. So in this case, maybe you're thinking, okay, we went from a ketone here to a alcohol, a tertiary alcohol, and you're maybe thinking like, oh shit, this is an easy like reduction question. So maybe I'll just use, law, or maybe I'll just use, I don't know, some kind of reducing agent like sodium borohydride. Well, that may be fine and dandy if this was just a simple like reduction question without this part. But if you notice, we added an ethyl group. So since we added an ethyl group, we know that this is an elongation of the carbon skeleton. So we're extending the carbon skeleton. We're adding, this R group here. So you want to think about like, what have you learned to add carbons? And we've discussed that in the previous class, that we've learned how to extend a carbon chain by doing one of three methods. Where did I place this? We learned it through either doing some kind of, acetylide ion extension via like chapter 9, where we use sodium amide to deprotonate, and then we did a simple SN2 reaction. Also we could have equally, hold on. Also, we could have equally done something like Grignard, which, where did I show that? Okay, well, we've learned to use Grignard. We've also learned to use an acetylide ion, and we've also learned to shorten a carbon chain by using some kind of ozonolysis. Here, what looks easiest, it's probably not going to be the acetylide ion. Hold on. It's probably not going to be the acetylide ion, because this wouldn't be an easy SN2 reaction, first of all. And second of all, there's no alkyne to start with. So the easy thing to notice is that we have a carbonyl with an electrophilic position here. It doesn't say, and it doesn't limit you on any kind of rules as what reagents you can use. So basically, all you have to understand, all you really have to understand is that we're adding this R group somehow, this R group, and we're going to add that R group via a Grignard reaction. And we've learned how to do Grignard reactions now. And if we were to start from just the simple ethyl group, this is an ethyl group, we would somehow first, need to add Br. And we've learned how to add Br with using NBS in light, right? That would add Br, okay? And there's only two positions, and there's no preference in terms of where that Br would add. Alternatively, you could just start it with this, if we don't give you some kind of rule to say like only start with a an alkyl halide, or only start with an acetylene molecule. Here it doesn't specify, so you can use whatever you want. Once we have that alkyl halide, this ethyl alkyl halide, right, we need to convert it into a Grignard, and we've learned how to convert that into a Grignard using magnesium and ether, correct? Once we use magnesium and ether, we form this Grignard reagent. This Grignard reagent, as we've said before, polarizes this bond in green, and it acts as if this carbon connected to the Grignard was acting like a carboanion, like a good nucleophile. And so let's say we take this Grignard reagent and we react it with our starting substrate, our starting carbonyl. So when we have a Grignard reacting with a carbonyl as such, this would be our first step. and our second step would be some kind of pronation step. And the reason for that is because upon this mechanism, we'll see that we'll need to pronate that alkoxide ion. But here, let me just erase this part just so I can show you the mechanism so it's a little bit clearer. We have this carboanion from the Grignard reagent attack this electrophilic carbonyl position. One of these bonds, this pi bond, is going to push up, donate those electrons to oxygen. Once that happens, you get this intermediate. This intermediate now has a negative charge on that oxygen. That's what we represent as an alkoxide ion. And then we're also adding this group, this ethyl group, to the molecule. So let's add that ethyl group in green. And we still have the other ethyl group from our parent structure, okay? And now this looks very similar to our final product. All we need to do is follow it up with our second step, which was water. Remember when I drew this with water? That's why we need the second step. Water or hydronium. It could be either or. You can write hydronium or you can write water. So once hydronium is in the mix, this acidic source, let me draw it this way. This acidic source now is a perfect provider of protons for the alkoxide ion to pick up, a simple proton transfer. And that is where we have a tertiary alcohol, that substituent, that R group that we added in green, and the other ethyl. And you can see now we've made our final product. So all you need to do for questions like this is understand, how are we elongating this carbon chain? We're elongating it by one of two methods, really. Either using an acetylide ion and an SN2 reaction, or using Grignard. And in this case, Grignard is the easier option. Why is it the easier option? Because we have a carbonyl. We have an electrophilic carbon position. We've made our Grignard reagent first by adding Br to our ethyl. Once we've added Br via NBS and light, we now have to create this alkyl halide into a Grignard reagent. We make this alkyl halide into a Grignard reagent by just adding Mg and ether. This now makes our Grignard reagent. Our Grignard reagent polarizes the bond between this carbon and the Grignard reagent. This makes this carbon act as a nucleophile. It attacks the electrophilic position, pushes the pi bond up, and it makes an alkoxide ion. We follow that out with an acidic source to be able to pronate this alkoxide ion to be able to make it into an alcohol. And that adds our alkyl group, our R group, this ethyl group that we added here, and it also pronates our alkoxide to make it into a tertiary alcohol. Okay? Not too shabby. All right. If there's no questions, I'm going to move on to this next question. Here, it's a three-parter. What we need to understand is what we're being asked, which I forgot to write down, is acidity. Which one is most acidic? Whoops. Which one of these, and each one of them, so we're going to treat them individually. Which proton is going to be most acidic? And tell me why. I'm not sure if we're going to provide you with a pKa table. Maybe not. If we don't have a pKa table, let's say you don't have a pKa table. What do you use? What rules do you use?
Cardio.
There you go, cardio. I hope everybody did their cardio today. At least 20 minutes every single day for a healthy, aerobic, cardiovascular fitness. So if you did your cardio today, what are we looking at? And we talked about cardio, right? We talked about charge, just to remind you, charge, atom, resonance, distance from inductive effect. inductive effect, and orbital, right? And we talked about that this isn't really like, it doesn't necessarily, it doesn't necessarily have to follow this order. Sometimes orbitals take more importance over atoms, right? And so that should be a prelude to why this question is a little bit tricky. What protons are we comparing? So if I was to label some protons, let's label 1, let's label 2, which by the way, this 2 and 3 are the same. So we can just treat this, I should probably put letters instead. Let's treat this as proton A. Let's treat these two because they're equivalent as protons B. Let's treat this ones over here because they're equivalent as proton C. And the ones over here as protons D. Out of these 4 protons, or 4 different kinds of protons, which one do you think is going to be most acidic? Or let's go by process of elimination. Okay, how about B? Why is B not the right answer? Anybody? Anybody at all? Think of what would happen if we depronated a proton on B. Hold on. So yeah, think of what would happen if we depronate a proton on B. Okay, we pick that up, we depronate it, let's say with some methoxide anion. Boom, we depronate that. Now we get something that has a negative charge, right, in this terminal position. Is there anything I can do with that negative charge? No, right? Because this carbon here in black has 4 groups. There's no resonance. It's connected to a carbon atom, right? And there's no charge associated with it. It's an sp3 hybridized carbon, right? There's nothing much you can do with that, okay? So we know that the protons in B wouldn't be our right answer. These protons B wouldn't be our right answer, okay? How about the protons located on C? If we depronated these protons, something over here, and this was depronated, and then we had a negative charge here. Let's put a negative charge here. If we had a negative charge here, let's make that in red. If we had a negative charge here, I mean, I guess we could technically like push this to the right, but could we push this to the right? Now we would have how many groups around nitrogen? Could we technically have done this? Is what I'm trying to say. Is this possible? And technically this would be 2 minus. Is this possible? Why or why not? If we push this here, is that considered resonance? Is that even possible? Anybody?
No, because it violates the octet rule.
Yes, ma'am, it does. This would violate the octet rule. Violates octet rule. So C is also no longer possible. So these protons in C are also not possible. So really we're comparing A and D. And if we're comparing A and D, okay, maybe I should just erase all this because it's getting messy. If we're comparing A and D, right? If we're comparing A and D, what seems more correct? Would it be nitrogen with the negative charge? Or if we depronated here, would it be the acetylide ion with the negative charge? Remember, if you don't have a pK table, you use the cardio rules or the REO rules. What do you think has more importance? Is it the orbital or is it the atom? Oh, let me give you a hint. Okay, so yes, this is on the more electronegative atom. More electronegative atom. Cool. But looky here, this would be sp hybridized. That carbon is sp hybridized. We talked about in chapter 3, if something is sp hybridized, that negative charge, wouldn't it be closer to the nucleus? Right? And since it's closer to the nucleus, what can we say? Is that negative charge more stable or less stable? It would be more stable, right? Since it's more stable because it's closer to the nucleus, this would be more stable since it's closer to the nucleus. That would make it, if you make a, anion that's more stable when it's deprotonated, that makes it more acidic, right? So here, all you have to determine is that, yes, even though nitrogen is the more electronegative atom, you see that this carbon is in an sp hybridized orbital. That negative charge is going to be closer to the nucleus. It's going to be the more stable anion. And since it's the more stable anion, it's going to be the more acidic proton. So A is going to be your more acidic proton. Okay. All right. How about B? B, what are we comparing? Make this easier for you. We're comparing hydrogens on A, hydrogens on B, and hydrogens on C. Tell me, what is more important in this case? Are we looking at atom? Are we looking at orbital? Are we looking at resonance? What are we looking at? We did a similar question, during our first exam review on something very similar to this. Actually, I can just pull it up. I think I still have it. Where was it? No, that wasn't it. Well, right now it doesn't matter. We'll just stick to this example, but I'll find it and I'll try to post it in the chat. But we did something very similar to this example. We talked about not only, okay, yes, oxygen. Is oxygen more electronegative than sulfur?
No.
Just look at, no, it is. Oxygen is more electronegative than sulfur. Oxygen is more up to the right than sulfur. It's not based on electronegativity. It's more so based on what is more, how do I put this? What has a higher or bigger electron cloud? It's more so dealing with orbital. If you look at S's orbital, what period is S in? If you look at your periodic table, what period is S in? Does anybody know? S is in the third period, correct? Does S have to obey the octet rule? So what I'm trying to get at is S is in a bigger period. It's in the third period, right? And because it's in the third period, it doesn't have to obey the octet rule. So first of all, it doesn't have to obey the octet rule. It's what we call an expanded octet. It's one of the exceptions. And because it has an expanded octet, it essentially has a larger shell. If you look at S, its p orbital is much bigger. Its 3p orbital is much bigger. Since it's much bigger, it's much more able to hold that negative charge. And because it's more able to hold that negative charge versus a smaller oxygen p orbital, let's say if this was oxygen's p orbital, this is 2p. Since it has a bigger p orbital, this bigger p orbital this bigger p orbital means that it can hold more electrons. Essentially, more it stabilizes the negative charge a little bit better. Okay, so the point here is looking at the orbitals, and it's not necessarily comparing like sp3, sp2, sp. It's literally comparing the size of the orbitals. Okay, so this is a little bit just trickier. This is just understanding, okay, which orbital is bigger and why. We see sulfur is a less electronegative atom, but it's in the third period. Its 3p orbital is significantly bigger than oxygen's 2p orbital, and thus it will be able to better hold that negative charge in its p orbital. Okay? All right, last question. This one. All right. What hydrogens am I comparing? What protons? Am I comparing these? Let's call this A. Am I comparing these? Let's call this B, C, or D? Out of A, B, C, and D, which one is the more acidic proton and why? Anybody? Don't be shy. Today and tomorrow are the days to ask questions.
Is it the double bond there?
It's not the double bond. Can anybody tell me why it's not neither B or C? Does anybody know? If I depronated B or C and had a negative charge here or a negative charge here, remember your cardio rules. Is there any resonance here? No, right? I wouldn't be able to have resonance with either B or C, nor would I be able to have resonance with A. So it immediately eliminates A as well. And these protons are too far away to have any kind of resonance as well. Because the carbons next to it, these carbons already have 4 groups. So out of logic, we know that it's D. And if we depronated one of the protons at D, this gets depronated again by some base, let's say. This depronates these electrons now in red form either, okay, so it can first form a carboanion. Let me just draw. It could form that carboanion, but then it could also push here, make a pi bond in red. And if it makes a pi bond in red, that would push these electrons from the original alkene up to here. So the resonance structure would look something like this. And because it has resonance, the protons at D are going to be more acidic because the negative charge is stabilized by resonance. Okay? Does anybody have any questions? So with these kind of questions, if you're not given a pKa table, refer back to your REO rules, or like we like to put it, your cardio rules. And these cardio rules aren't set in stone by which one, like if charge comes first before atom, before resonance. You have to look at the intricacies or the nuances of acidity. Acidity basically says that if we depronate one of these molecules, if we take away one of those hydrogens, where are we forming the most stabilized negative charge? And so if we look, for example, with the first example, even though nitrogen is a more electronegative atom compared to carbon, this carbon is sp hybridized, meaning that its negative charge is closer to the nucleus, meaning that since it's closer to the nucleus, it's going to be more stable, therefore being more acidic. In the second case, we looked at two different electronegative atoms, oxygen and sulfur. We know that oxygen is much more electronegative than sulfur, although sulfur is in the third period, meaning that has a bigger p orbital. That bigger p orbital can technically have more electrons. That's what we call an expanded octet, and therefore first of all, doesn't obey the octet rule. And since it has a bigger p orbital, it's going to have much more room to hold that negative charge. So it's going to be more acidic on sulfur. And lastly, just determine, okay, which one of these carbons, none of them have a charge. They're all on the same electronegative atom, carbon. But if we see here, the protons in D, which were placed at this apex, once we depronated that, this negative charge, this carboion now has resonance via this pi bond. So once you form this pi bond here, you push the electrons in red up here and form a resonance structure. And because it has resonance, it's going to be a little bit more acidic than either the protons that are originally on B or the protons that are originally on C. Okay. If nobody has questions, I'm going to move on to the next question. All right. Let's push this up. And now we have this kind of chapter 9 question. Okay. What have you guys learned from chapter 9? Let's look. We have excess HBr, and we're given a couple of choices. Excess HBr, what does that do? Or before reading the excess part, what does HBr do? Anybody? HBr adds, as the name implies, it adds a hydrogen and a bromine. But where does that bromine add?
The bromine goes onto the Markovnikov side, right?
Yeah. Bromine adds Markovnikov, or to the more substituted side, right? The more substituted side. Okay, so here we're using excess HBr. With excess HBr, are we forming what I would like to call, so here's the thing. Are we forming a geminal dihalide? Or are we forming a vicinal dihalide? When you use HBr with alkynes, what are you getting? A vicinal or a geminal dihalide?
Is it geminal?
Yes, it is geminal. Okay, so here's the reason. It is geminal. So it is geminal. That is correct. Because if you were, let's say you wanted to do it vicinal, you would have to use Br2 Br2 and carbon tetrachloride. Remember, that would produce Vesinol because it adds 2 carbons opposite to each other, right? And here we're only using excess HBr. And so excess HBr adds a bromine Markovnikov, or to more substituted side. So we know that if we just added 1, let's see, if we just added 1, okay, whoops, missing a metal. If we just added 1, we'd get this product, right? But since we're adding another HBr, we have to add the other HBr to the more substituted side, right? And so what does that look like to you? It's tricky. So we can eliminate the Vesinol dihalide, which Vesinol, I don't know if you guys know a little bit of Latin. It's technically for neighboring halides. And geminal technically means same, like same carbon. That's what the geminal means. Okay, so if we're adding to the most substituted side, do we have an answer? And we know that it's not doing this. We know that it's not doing this because it's excess. You know that it's not doing this, again, because it's excess. This would work if this was 1 equivalent. This would be 1 equivalent. 1 equivalent HBr, right? What would this be? Can anybody tell me what reagents we would use for this, for option B?
HBr with peroxide.
Yes, sir. Thank you. HBr and peroxide. And we just said that if we wanted to do this, we would have to use Br2 and carbon tetrachloride, right? So now let's look at our answers. DNE. All right, since it's HBr, right? This adds Markovnikov. We count our carbons. Easy way to do this is just count your carbons. If you were to count your carbons from this position, we would have 1, 2, 3. Now let's count our carbons. Do we have the same carbons? From this position, 1, 2, and 3 versus this position, 1, 2, and 3. It seems that we have the same carbons, and they both seem to be geminal. This is geminal, and this is geminal. But now all you have to understand is what we said in the first step, is that HBr adds bromine Markovnikov. And since it adds Markovnikov, it adds to the most substituted side. This would be internally at carbon number 2. So that would be at carbon number 2. Where's carbon number 2? Here's carbon number 2. Here's carbon number 2. So we know that our answer would be D. Okay? So just a quick recap. We first identify our reagent. Our reagent is excess HBr. We understand that HBr adds bromine to the more substituted side. So once we know that it adds more substituted side, and it's also going to add, HBr is going to add geminal, we look at our answer choices, we count our carbons, 1, 2, 3. We look at our, hold on. After counting our carbons 1, 2, and 3, we look at which one would have added to the internal position, to the more substituted side. That would be answer D. Okay? Any questions? No? All right, moving on. All right, very similar, good chapter 9 review. All right, so here it says, select the best reagents for the reaction shown. What kind of reagents are we seeing? Which ones, what do they do? What would make the most sense? So right off the bat, we know that we're forming a what? What is this group called? Anybody? What's that functional group called?
Ketone.
It's not a ketone. Why is
Aldehyde.
it is an aldehyde, because here at that carbonyl carbon position is a hydrogen. It's not an alkyl group. Okay, that's the first thing you have to identify, because that's going to influence our choice. Our choice is basically saying, okay, which one of these makes an aldehyde? And if you look, you can also, again, count your carbons. This is a terminal aldehyde. Let's count our carbons from this position. We have 1, 2. From that position, we have 1, 2. There's no more carbons past 2. So we know that it added to the terminal position. Because it added to the terminal position, which one of these reagents do you know makes a carbonyl, or in this case, because it's a terminal alkyne, makes an aldehyde at the least substituted side?
It's a hydroboration.
Yes, it is hydroboration. It's hydroboration, and we can eliminate basically A, C, and E, because those all do different things. You know, this adds 2 OHs, right? We don't see that in our group. This splits, you know, this is ozonolysis. That's not what's happening, ozonolysis. And this saturates. This wouldn't also work. So we're looking at hydroboration or oxymercuration, demercuration. And because we're going to the least substituted side, the position number 2, we're making an aldehyde. That would be hydroboration. And I want to ask one more question. If I was to accidentally pick B, you know, erroneously, let's say I picked B erroneously, what would our B product be if I used, you know, oxymercuration, demercuration with this? If this reagent was oxymercuration, what would our product look like? Or what functional group would it be?
Ketone.
It would be a ketone. So it'd be almost the same thing, right? But it would be a ketone. Does everybody see that? We added that carbonyl at carbon number 1 instead. Right? This is carbon number 1, this is carbon number 2. So it's basically saying, okay, where are we placing the carbonyl? Are we placing it internally or terminally? And we know that in this product, we placed it terminally. So we needed to do hydroboration, right? But if it was placed at carbon number 1, we would pick answer choice B, okay? And this is just a long-winded way to say that there's a regioselective preference. There's a regio preference when it comes to using these reagents. So here we're looking at, like, basically I'm asking which one is regio selective in this case. Is it A or is it B? Okay. And there's another question very similar to this, which let me see if I can find, because it just illustrates the point that sometimes there's no regioselective preference. Let's see if I can find it real quick. So this is chapter 9, right? So this is at the end of chapter 9. At the end of chapter 9, there's a very similar question. Where is it? Just had it. Damn it. Maybe I can find it later, but I really kind of wanted to show you guys. I can't seem to find it. I mean, I can make something up. It doesn't really matter, but I'm trying to illustrate the point that when there's no regioselective preference, it doesn't matter where you make the carbonyl, and you could technically use both. Here, let me just draw you a quick example of this. Let me make something up. So, for example, let's see. If I had something like this, and I told you, let me see how many carbons I could draw. 1, 2, 4, 1, 2, 3, 4, 5, 6, 7. Yeah, do something like this. This is gonna be a little ugly. Ugh. All right, this is not the best looking molecule, but let's say I had something like this. And I told you, all right, I want you to either make a ketone here or a ketone here. It doesn't matter what reagent you would use. It doesn't matter if you used oxymercuration, demercuration, or if you used hydroboration, because the point is that there's no regioselectivity. There's no regioselectivity when there's a symmetrical atom and the alkyne is internal. So when you had something like this, let me just copy this, this would be easier. If I just had something like this and I told you to basically do hydroboration or oxydemercuration, well, guess what? They form the same product. You could either form a ketone on this side, or you can equally form a ketone on the other side. The point here being is that you could use either reagent. You could use either reagent, either oxymercuration or hydroboration, to make one of these two ketones. These are equivalent ketones. So the point with something like this is that if you have an internal alkyne, if you have an internal alkyne and the molecule is symmetric or symmetrical, this means that there is no regioselective preference. And what that basically means in plain English is that if you have something that's an internal alkyne, and there's no other substituents on there, which there wouldn't be, especially when it's something that's symmetrical, you can't tell whether it's anti-Markovnikov or Markovnikov, more substituted or less substituted, because it's symmetrical. You could use either of these two reagents. So either reagent would be possible. Okay. And don't worry about actually like writing all this down. I'm going to share the PDF once we're done. And after a couple hours, it's going to process and you're going to be able to watch this recording anyways. Okay. All right. Synthesis. Let me push this down. I might need more space. Okay. Quick synthesis question. Or actually, yeah, this is synthesis. This looks tricky, but it's really not. All you have to understand is use your tool belt. We've learned a couple different ways to, break rings. And the only reaction that you guys really learned was ozonolysis, right? We use ozonolysis to be able to break a ring in half. But to break a ring, notice, so first off, I want you guys to count your carbons. Notice how many carbons we have. How many carbons do we have in this? I should ask, do we have the same amount of carbons in our reactant and in our product?
No.
No? Are you sure? Let's count.
We do.
Yes, it's 6.
Okay, because I was gonna say there's 1, 2, 3, 4, 5, 6. Okay, and here we have 1, 2, 3, 4, 5, 6. Right? So we're not extending our carbon skeleton, but what are we doing? We're breaking that ring. All right. This is not a mechanism question. But how would you break this ring? I'm going to go in the forward direction. How would we break this ring? Anybody? What's the first step we have to do? I told you that we're going to break the ring. I've already explained to you that we can break a ring by using ozonolysis. But how did we learn to use ozonolysis? We needed something before we did ozonolysis. Does anybody have any ideas? Think back to chapter 8. To use this reagent O3 and DMS, we needed something. We needed to start with some kind of functional group. What was that functional group? Go back to chapter 8. Just think about it. Like ozonolysis broke some kind of bond in half, and we added
Double
two
bond.
a double bond, an alkene. We need an alkene. An alkene is needed, but we don't have an alkene in our reactant. So how do we make an alkene? We make an alkene from an alkyl halide using what? Or I should say, what kind of alkene do we need? Do we need this alkene? Or do we need this alkene? Do we need the Hoffman alkene? Or do we need the Zaitsev alkene?
Is it the Zaitsev?
Yes, yes, we do. And you'll notice we need the Zaitsev alkene because we have a ketone. This methyl group 1 is this group over here. I don't know if you guys can see that. That's what that group represents. We formed a carbonyl, but it's a ketone. This is a ketone, right? And this carbon that I'm showing in 1 is this carbon, is this methyl group here. I don't know if you guys can see that. So here, let me make this a little bit clearer. So, all right, whoever just answered, give me the reagents you would use to make the reactant, this molecule, into a Zaitsev alkene. Are we using small base or are we using bulky base?
Okay.
No, because if we did bulky base, we would get to our Hoffman alkene. Right? That would be an E2
Oh, yeah,
elimination.
yes.
Right. So we have to use a small base. All right, let's use a small base. What kind of small bases do you know?
NaOH.
NaOH is fine. Methoxide is fine. Any small base you can think of would be fine. NaOH is good. What's even better is methoxide. So something like this and a solvent like methanol. Okay, so this, using a small base, we would get this product. Right? And I already gave you the second step. What's our second step? What's our second step, guys? We're breaking this ring. How are we breaking? Ozonolysis, right? Yeah. Okay, so it's O3 and DMS. Okay, we break the alkene. And wherever we break the alkene, we're going to form a carbonyl, right? So let me just copy this, duplicate, and I'm going to make this a little bit bigger so you guys can see. So if we break that alkene, this is what's going to happen. If we break that alkene, now we're forming shit. We're forming two carbonyls, right? Does everybody see that? Yes? No? Maybe so? Say yes. Okay, so here, now let's make this a little bit prettier. And let's notice something too. 1, 2, 3, 4, 5, 6. Our carbons haven't changed. Now, all I'm going to do to this is I'm going to flip it. Okay, so I'm going to flip this molecule. So if I flip this molecule, it would look something like this. Flip this molecule, it's going to look something like this. Yeah, this is a little ugly. That's better. Slightly better. Okay, we're going to flip this. And now I'm going to bring this whole carbon skeleton down. Okay, so we still have the same number of carbons. 1, 2, 3, 4, 5, 6. But I'm just going to make it more linear. So I'm going to bring basically this carbon skeleton. Let me highlight it. This carbon skeleton, I'm going to bring it down. I'm going to bring this down. So now it's going to look like this. 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. Now, does that look like our product? We're almost there, right? We're very close. Let me copy this. We're almost there. And let me just finish the stop bubble. After this step, this is what happened. Okay. So what's our last step, guys? What do we have to do to this?
OH.
We have to add this OH where this hydrogen is. Okay. What do you call that? When we're looking at that carbon position, let's show it. This carbon position, is that carbon, is it becoming oxidized? Is it becoming reduced? Is it neither? Is it both?
Oxidized.
Oxidized. Good job. Okay. And what would we be using to oxidize this? We learned that we can take an aldehyde and oxidize it even more. Excuse me. We can oxidize it even more using what kind of reagent?
Is it the chromate?
Yeah, it's just simple chromic acid. So if we use chromic acid, and chromic acid, what was it? Na2 something? Na2 Cr2. O7, and this is in sulfuric acid. Sulfuric acid and water. So we've oxidized this carbon, or this carbon, sorry. This has been now oxidized. Oxidized. All right, but does that do anything to this carbon in orange? Why or why not? Okay, so this is the point. The point is this carbon in orange does not become oxidized. Does not, that looks ugly. Does not become oxidized. Become oxidized because it's already a ketone. Already a ketone. And the reason is because this ketone, this alkyl group here, this alkyl group cannot be kicked out. This is not a good leaving group. This methyl group, this alkyl group cannot be kicked out. It's not a good leaving group. So you can't oxidize this, okay? Technically, you could oxidize this if it was something else. If this was like a good leaving group, like chlorine, or maybe like an ester, you could kick it out. But because it's a ketone, and more specifically, it's an alkyl group, it's not a good leaving group. This is not a good leaving group. Therefore, it cannot be oxidized any further, okay? So quick recap, just to, beat a dead horse. We saw that we did not change the number of carbons. We have the same number of carbons in our reactant, or in our reactant to our product. We counted 6, and there's 6 on both sides. We know that we were breaking this pentane ring. And to be able to break that pentane ring, we have to think about what reactions we use to be able to break things in half. And not only break things in half, but at the same time, form 2 carbonyls. And we learned that we could use an alkene and then use ozonolysis to be able to break one of these alkene bonds in half. And when we do that, we get 2 carbonyls. But we had to determine which alkene we would use. And we decided to use our Zaitsev alkene because that gets us closer to our product. We didn't pick the Hoffman alkene. Why? Because the Hoffman alkene would have made this product. It would have made a ketone, and then it would have made an aldehyde, right? These were the 2 products if we used ozonolysis. If we use O3 and DMS, this is 1, this is 2. Oops, let me just draw this a little bit better. If we use ozonolysis with the Hoffman alkene, we would get this ketone, which, as I stated before, we could not further oxidize. We cannot further oxidize. And we would have gotten an aldehyde. This aldehyde. So that wouldn't have worked either. Okay, and we just shortened. If you also notice, we've just shortened our carbon chain. Okay, so we know that we're not using our Hoffman alkene. We know that we're not using our Hoffman alkene. So we understand that we have to use our Zaitsev alkene. To get our Zaitsev alkene, we know that we have to use a small base. We use the small base like methoxide to be able to get our Zaitsev alkene. Once we got our Zaitsev alkene, then we use ozonolysis to be able to break that alkene in half. Once we broke that alkene in half, we formed 2 carbonyls here at positions 6 and 2. Once I flip that, basically vertically, I have this molecule. And all I did was bring this carbon chain down to make it linear. Okay, once we made it linear, we realized that we had a ketone and an aldehyde. Once we have that ketone and aldehyde, all we had to do is compare this intermediate with our final product. We noticed that this carbon in green was oxidized. To be able to oxidize that carbon in green, we will be able to kick out that hydrogen and oxidize it with more basically more CO bonds. And all we had to do here was use chromic acid to oxidize that terminal aldehyde. And we didn't oxidize this ketone because we cannot kick out an alkyl group, specifically this methyl group at carbon number 1. Okay? That was a lot, but you know, if you rewatch this or if you practice, there's more questions just like this at the end of the chapter. Okay? All right. Mechanisms. I know you guys like mechanisms. So let's do some mechanism questions. Talk to me. What am I doing first? What do you guys notice with this mechanism? What are we doing? What are we doing? What's disappearing?
The double bond.
Correct. So if the double bond is disappearing, I must have somehow saturated that double bond. Do you notice anything else?
Increase in carbons.
Is it increasing in carbons? Let's count. Let's just make sure. So we have 6 carbons here. 1, 2, 3, 4, 5, 6. We have a carbon here, 7. We have a carbon here, 8. And we have a carbon here, 9. Let's look over here. We have 1, 2, 3, 4, 5, 6. We have a carbon here, that's 7. We have a carbon here, that's 8. And we have a carbon here, that's 9. Have we extended the carbon chain? No, right? So we have the same amount of carbons, in our reactant and in our product, okay? So we know that we're not extending the carbon chain. That's good. That's a good first step. So we know that the alkene is leaving. So we notice alkene is leaving. Alkene is leaving. Okay, how are we like making that alkene leave? Well, we talked about this hydronium is an acidic source. And what I'm trying to say, it's a source of protons, right? So this source of protons is essentially going to saturate that alkene. And so this is just a simple proton transfer. Alkenes are a good source of electron density, right? That electron density, basically, these 2 electrons are going to pick up this proton. And where is it going to add? Answer me this. Is it going to add at carbon number 1 or is it going to add at carbon number 2?
2.
2. Why? Why does it add at carbon number 2? You're right. It adds at carbon number 2. Or no, sorry, it doesn't add at carbon number 2. Okay, but tell me why it doesn't add at carbon number 2. So if it added at carbon number 2, what would happen to carbon number 1? Look at the implied hydrogens. The implied hydrogens here are 2 hydrogens, right? So now if that carbon only has 2 hydrogens, wouldn't there be a positive charge here? Is that what we want? Think about it. We talked about, you know, primary, secondary, tertiary carbocations. Remember, instability. We don't want to make a primary carbocation, right? So it won't add at carbon number 2. It adds at carbon number 1. So let's fix this. Okay, fixing. We know that it's going to add at carbon number 1. And let me draw this in red. Carbon number 1 and number 1 still has those other 2 hydrogens. All right, now we formed a positive charge at carbon number 2 because carbon number 2 only had 1 implied hydrogen, right? So it now has a positive charge at carbon number 2. What can we do to this molecule to make it more stable? So to the person that before,
Methyl transfer?
yes, a methyl shift. To the person that was asking before, do I do a hydride shift or a methyl shift? Or a methyl shift, and when to use one? You have to look at what happens when you do a hydride or a methyl shift. So at this carbon in green, is there a hydrogen that we could shift? No, right? Because it already has 4 groups. 1, 2, 3, 4. Okay. And would it make sense to shift this hydrogen in red here? No, because we would go back to our primary carbocation position, and that doesn't make sense. We're not making it more stable. So yes, we will do a methyl shift. So Joseph, correct. You will do a methyl shift. We will do a methyl shift. So we're going to shift this methyl over. All right, let's draw that now. Once we shift that methyl over, we get this position. Now the positive charge is here. Cool. Are we almost to our product? Basically, right? We know that when we depronate hydronium, remember this was essentially, this proton source came from hydronium, right? And once that happened, these electrons were donated back to that oxygen, this now formed water, right? Since it now formed water, couldn't we have water come in? Water now comes in and attacks this electrophilic position, right? That's how we get the hydroxyl group to add there. We get the hydroxyl group to add there, but there's one little problem with that, or there's one missing step with that, right? Because if I do this, well, now look, we have a hydroxyl group. It's now been added, but it has 3 groups and only 1 lone pair positively charged. What have you learned? What can we do to this to make it a hydroxyl group?
Is
To
it
stabilize
proton
it?
transferred to water so you get
Yes.
H2O plus?
Well, this is H2O plus now. Right now, this
You
is
would get
H2O.
OH.
Yes, we take
Yes.
another water molecule. We take another water molecule. We bring in another water molecule. We bring in another water molecule to depronate that water molecule that attacked. So these electrons donate back to oxygen. And now you form your final product. And oxygen is now happy with both of its electrons, or both sets of its electrons. So real quick, we noticed that the alkene was leaving. We said that alkene is leaving. And we also said that we're not changing the carbon skeleton. It's the same amount of carbons in our reactant and in our product. We counted them. It was 1, 2, 3, 4, 5, 6, 7, 8, 9. Same thing in our reactant. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, cool. So now we focus on making alkene leave. We make the alkene leave by saturating the alkene. We saturated the alkene with a good proton source like hydronium, and we decided where is that hydrogen going to be placed? Is it going to be placed at carbon number 1 or carbon number 2? We said that it was going to be placed at carbon number 1 because it would make a secondary carbocation, which is more stable. We placed that hydrogen at carbon number 1. We formed a carbocation at carbon number 2. We were saying, what should we do? A methyl or hydride shift, right? We decided on doing a methyl shift because it would make a tertiary carbocation, which is even more stable. And we decided not to do a hydride shift, because if we did this hydride shift and put it here, we would go back to a primary carbocation. That's not what we want to do. So once we formed that tertiary carbocation, all we had to do was attack it with water. Once water attacked, it is now basically a water molecule that has a positive charge. It's very close to our hydroxyl group here in our product. All we had to do was depronate one of those hydrogens from that water molecule using another water molecule. And then we got our lovely stabilized product with our new hydroxyl group. Okay? Easy? Easy enough. All right. Moving on. So, all right. Very similar to the question that we've already done. But you guys tell me, what do you noticed here? Okay. We've already talked about the different reagents. This, what is this? Is this, what kind of reagent is this? Name the reaction.
Acid catalyzed hydration.
Yes, it's what do we call this? Oxymercuration, demercuration. It's this like the same thing, right? And what does this have preference for? The internal or external position? Is it here or is it here?
It's Markovnikov on the inside.
So it'd be at carbon 1 instead of carbon 2, right?
Yeah.
So, and what does that first product look like? What does it make, I should say? What functional group does it make?
It adds an alcohol and a hydrogen.
Yeah, but after the second step, what does it make? Because that's only the first step, and it still has the alkene. But what's the what's the whole thing? What's its major product?
Ketone.
Yeah, it's a ketone. So let me draw the first product. 1, 2, 3. Right? So now I'm treating this with sodium borohydride and methanol. What does sodium borohydride do? Does it oxidize or reduce it? And based on your choices, you should be able to oxidize or reduce. I mean, it should be obvious to you since I gave you the choices. Clearly, you're making an alcohol, so that must be reduction. So sodium borohydride with this carbonyl reduces, and it reduces to an alcohol. All right, let's look at the position where it's reducing. And if you count the carbons, 1, 2, 3, just like in our original structure, let me just change the numbering. 1, 2, 3. We made a carbonyl here. We agreed on that. This is the carbonyl. And then we're going to reduce it to an alcohol at that same position. So if we reduce this to an alcohol at the same position, we see why one of these choices is correct or incorrect. This, our product, looks just like the 1 and 2, right? 1, 2, 3. We made a carbonyl at 2, and then we reduced it to an alcohol, right? All right, cool. That's all fine and dandy. Question or answer choice 3 is completely wrong because that added at position number 1, right? And we agreed that this either makes a ketone or a carbonyl rather in the internal position on the more substituted side at carbon number 2. But what if I mix this up and I said it was choice 1? What would this reagent have to be to make choice 1? Because this reagent is fine. But what would that reagent, if you chose choice 1 erroneously, what would be your first reagent? What had to have happened to be the first, like what was the first reagent instead? Basically the opposite of what we just did. Instead of adding the
Is it
carbon.
hydroboration?
Yes, exactly. That's the simple, like that's the
Yeah, because
that's
it's
what
anti-Markovnikov.
exactly. So it would have had to have been hydroboration, which is like I think you guys learned R2BH or something. You could have also, if you forget the reagents, it's on your reagent sheet. But if you wrote BH3 THF in what is it? I always forget, peroxide and some base, either answer is acceptable. Okay. So yeah, that's just to say this is BH2. No, it's R2BH, I think, and the same peroxide and base. Okay. So if you were to decide to have picked 1, you would have technically needed to use hydroboration. Okay. And that's as simple as these questions get. Okay. Moving on. All right, another very simple alkyne question. And this should give you a hint. We're gonna use some of chapter 9 on this exam, or lots of chapter 9. And this is almost the same question. I should have changed this up, but very quickly. Okay, give me the answer. How would you go about this? Walk me through this. This is literally the exact same question, or yeah, this is almost the exact same question, basically the exact same question. The only difference here being is that we have 1 less carbon, but we're using the same steps. And I should have chosen a different, I should have changed the reagents a little bit. But you see, okay, we make in our first step a carbonyl at this position. If we make a carbonyl at that position and then we reduce it, we would get a secondary alcohol. Which one of these choices has a secondary alcohol placed at the internal position? It's definitely not D. It's definitely not E, because that will just be the first product.
B.
B, exactly. So I just want you guys to quickly understand, if you see, either of these 2 reagents, whether it be oxymercuration, demercuration, or whether it be hydroboration, you understand which side of the alkyne you're picking. Unless it's like one of these questions where there is no regioselectivity, there's no preference in where you place that carbonyl. In this case, there is a preference where you place that carbonyl. It would be internally. You make first, technically would be this product. You make a ketone first, but then you actually reduce that ketone to make a secondary alcohol. Okay. Cool. All right. Now we have a whole bunch of synthesis questions, and I should have probably made these here. I know what I can do. I'm gonna cut these into chunks. So we'll do the first one. There you go. We'll cut these into chunks so we can do a couple. All right. So starting off with the first question, this is, I forgot what chapter this is from, but this is just simple synthesis. Talk to me. What are we gonna do with these synthesis questions? What are we making? We're making a ketone, right? How are we gonna make that ketone? What's our first step? Notice that we're adding carbons. right? We're adding carbons. Okay, cool. How many carbons are we adding? All right, here we have 1, 2, 3, 4 carbons. Here we have 1, 2, 3, 4, 5, 6 carbons. So somehow we added 3 more carbons. Interesting. Okay, how are we going to add those 3 more carbons? All right, let's make this a little bit easier. In this case, let's go backwards. I think backwards would make it a little bit more simple. All right, we've already beaten this like with a dead horse. I can make a ketone. I can make this ketone from an alkyne, right? From an alkyne. Okay, so we can make a ketone from an alkyne. We could also make it from an alcohol. And essentially, like, I think the alkyne would be an easier step because we're going to have to add carbons. And we know that we can add carbons using the acetylide ion. So here I want you to think, okay, I added how many carbons? So this was 1, 2, 3, 4, and I added 1, 2, 3, 4, and I added 2 carbons, 5 and 6. So I added 2 carbons, and guess what? Acetylene has at least 2 carbons. And we also said that alkynes can form ketones via oxymercuration, demercuration, right? So let's say we started backwards. This is retrosynthesis. We're starting backwards, okay? And since we're starting backwards, we can say that we made this product from an alkyne. We made this from an alkyne, right? So now let me draw the alkyne. That alkyne would look something, let's use black, would look something like this. I mean, it doesn't have to be perfect, but so now let's count. 1, 2, 3, 4, 5, 6. Cool. We started from an alkyne. Great. And we said we needed what? We needed oxymercuration, demercuration, which was H2SO4 and water and that like mercury sulfate acid, right? Okay. That was our first step because we know that we're going to add a carbonyl in that internal position. There's regioselective preference. That's where that carbonyl is going to add. Cool. We've gotten up to here. How did we add this alkyne? Or rather, I should say, this is the alkyne. How the hell did we add this group? Let me see if I can make this a little bit clearer. So let's say I had this alkyne. I have this alkyne, right? And I wanted to make this, right? I'm adding something to this side, right? What would I need to do to first make it into the acetylide ion? So first I have to make the acetylide ion. First, make the acetylide ion, right? Which will depronate this group, this hydrogen. So if I did that first, I would have to make this acetylide ion, right? And to go from here to here, we just use sodium amide, right? Once we have that acetylide ion, maybe I should have drawn this the other way, but once I have that acetylide ion, what can I do to that acetylide ion? I'm going to draw it this way just to make it clear. How can I add that group here that I'm highlighting, this group? How can I add this group? Oh, this is an SN2 reaction, guys. Remember? And then we can use an SN2 reaction with what? Could we have just used the starting material? This? No, right? Because one, you don't do SN2 type reactions to a nucleophile or to an alkene. That doesn't make sense. You would have to make it into what kind of group? We would have to have a leaving group, correct? We would have to have some kind of leaving group. Why is it not writing? Okay, we would have to have some kind of leaving group. So here, there would have to be a leaving group. Why? Because we're going to nucleophilic attack this. We're going to nucleophilic attack this here at this position, and the leaving group is going to leave. That's going to create this alkyne now connected. Let me draw this a little bit differently. Now connected. Yeah, why is it not doing it? Here we go. It's now going to be connected to that group, right? That looks very similar to what we just had. Remember, count our carbons, 1, 2, 3, 4. Now we have 5 and 6. So after this SN2 reaction, we get our pentultimate product. Does everybody see that so far? But first, we had to have made this good leaving group at the last position. And if we look back to, this is why sometimes it's easier to start in the like forward direction, but it would have been a little bit too complicated to show you like without having you understand all the different steps and all the different nuances why we picked an alkyne instead of picking something else. How do we make this into, so I'm asking, how do we make this group into this group? What's a good leaving group?
HBr with
Yeah.
peroxide.
There you go, HBr and peroxide. HBr and peroxide does this in one step. It adds Br to the least substituted position. And Br is a good leaving group. That's what I'm trying to get at here, is that we need to have a good leaving group. We need to have Br and able to do this SN2 reaction. Okay? So what you had to do first was make this into a good alkyl halide. You made this into a good alkyl halide by adding HBr and peroxide. This makes a good leaving group. This bromine is a good leaving group. Then we take acetylene. We take this acetylene molecule. This acetylene, we have to first treat it with sodium amide to able to deprotonate this hydrogen. Once we deprotonate that hydrogen, we now have the acetylide ion. This acetylide ion, I already wrote it. This acetylide ion. Here, we already made this acetylide ion. Cool. Once we make that acetylide ion, we can now have an SN2 reaction to be able to extend this by 2 carbons. These are the 2 carbons that we're adding. This group here is the same as this group over here, right? All I did was flip it. All I did was flip this molecule. I flipped this. All I did was flip this. Once I flip this, guess what? These are the same reactions that we've been doing in all these previous questions. We used an alkyne to make a ketone by adding to the internal side, to carbon number 5. Do you guys need a further explanation? I can go through this, here, let me just, okay, so the first thing we identified is that we extended this carbon skeleton by 2 carbons, okay, and we added a functional group. We added ketone. And so we know how to make ketones. We can make ketones from an alcohol, but equally we can make ketones from an alkyne. We decided to use an alkyne because we have to add 2 carbons eventually, because we went from 4 carbons to 6 carbons. So it's easier to use an alkyne to be able to make this ketone. So cool, we have to use a terminal alkyne. We use this terminal alkyne, but this alkyne originally came from an acetylene molecule. We use an acetylene molecule, we depronated it with sodium amide to be able to make it into a good nucleophile. This is now a good nucleophile. This is a good nucleophile to do an SN2 reaction. This SN2 reaction attacks at this primary position, this primary substrate position, kicks out the bromine, and now adds this whole group that's been highlighted to the acetylene. Cool. But how did we make this alkyl halide? We made this alkyl halide by just simply adding HBr and peroxide to add Br to the least substituted side. So all you had to do was add HBr and ROR to get this bromine, which is a good leaving group, to add to the least substituted side. Okay, that made our good alkyl halide. We took an acetylene molecule, we depronated it, made it into a good nucleophile. We did an SN2 type reaction where we attacked the primary substrate, got rid of that bromine. Now we've added these 2 extra carbons. We flipped that molecule around just to make it more clear. Now we have this terminal alkyne, and all we had to do to this terminal alkyne is treat it with oxymercuration, demercuration, or an acid catalyzed reaction to be able to add this ketone to this internal carbon number 5 position. All right. I know it's a lot. I don't mean to scare you guys, but you should practice your synthesis if you're not yet comfortable with these kinds of reactions, okay? Here, we have a very, very similar situation. This is almost the exact same situation in B. Let me push all these down. And I still have to do, I might not get through all of these, to be honest, because I have to go over at least question number 5. So we'll see. We have 7:35. We have 25 more minutes. Okay. These are low priority. This is, I mean, if you watch the recording, I did something similar to both of these questions, but I wanted to go through at least one more mechanism. So how about this? I'll do, I mean, these are all kind of similar questions. I'll do B, and then I'll do question number 5, and then we'll see what else we have left, or what else we can get through. So let me just copy this. Copy. Let me move this somewhere else. Move. And then add this question. All right. Here, what's the difference with this? Basically, it's the same steps. It's almost the exact same steps. Can anybody tell me what is the difference between this product?
It's the ketone is on the external carbon.
Thank you. So that ketone is now placed at the external carbon. And let's just double check, let's double check our math. So we have 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, and we added 5 and 6, right? So we extended the carbon skeleton by at least 2. And like you just said, we added this basically to the external position of that carbonyl, right? Or of that alkyne. correct? So we had 1, 2, 3, 4, 5, and 6, and we added it to the 6th side, to this terminal side. And so what are we adding? What reagents are we adding to this to make that possible?
R2BH.
Keep going.
I don't know.
Okay, it's fine. You're gonna have a reagent sheet. So just look at the reagent sheet and just identify what reagents you're using. But this is the same thing as hydroboration. Okay, so from here, all we did, because this is this at carbon number 6, this is an aldehyde, right? All we did that was different from A was basically just added it to the least substituted side to carbon number 6 instead of carbon number 5. So all we have to do is essentially the same process. All of this, basically all of this jazz, to do the same, to get the same steps. Do we see that? Yes?
Yes.
Okay, cool. So that makes my job a little bit easier. I'm going to keep these last 2 questions. Maybe I can copy these. And if we have time, or if you guys want to try them out on your own, and then text me or put it in the group chat, me and Eric will check to see if you guys are correct. Okay. But if you've been doing the end of the chapter questions, you'll realize that you may have already seen this and you may have already done this. So let me move on to, I'm not going to do these first. I want to do this question first. And then maybe the challenge question. This is the challenge question, but this is also from your book. So you could also just look at your book, but here, this is from Salome's previous exams. And this is a little tricky of a mechanism because we're using a bicyclo. But I just want you guys to get more practice with mechanisms, especially if we're using something like a bicyclo. In this case, we notice that the OH group is leaving, right? OH group is leaving. And somehow an alkene is appearing here. So OH group is leaving and an alkene is forming. What do you think is going on? Are we getting rid of any carbons? So let's just make sure that we're not getting rid of any carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. Let's just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So we didn't get rid of any carbons, right? That's good because this is a mechanism question. That would be a little bit tricky if we got rid of carbons. Now we notice that the OH group leaves, the hydroxyl group leaves, and we formed an alkene. So what would be our first step since the OH group is leaving? I know you guys are tired. I'm tired too, but you know, we're almost done. Just OH group leaves. So what are we doing? What's the first step? No? Anything? Anybody want to help me out? Is OH by itself a good leaving group?
Is it HBr?
No, this is a mechanism.
It's gonna be a proton transfer to turn it into water.
Yes, this is a mechanism. So it's not HBr. We're only using the reagents that's listed. So you're correct. We have to do a proton transfer with the electrons, that lone pair of electrons that's on oxygen. We have to pronate this, right? And we said that hydronium is a good source of protons, right? That good source of protons is going to pronate that water molecule. Cool, let's draw this again. Okay, now it became a good leaving group. Let's say it does leave. what's gonna happen? Shit, if it leaves, what forms? Okay, so that leaves. Now what are we forming?
A primary carbocation. So then you'd add it to that right side of the cyclo compound.
So let's duplicate. Water left. And oh shit, we formed a primary carbocation. Damn, do we want to do that? Yikes, right? We formed a primary carbocation. Fuck. What do we do? Like, can we do a methyl shift? We have to look at the adjacent carbon. Here, is there any methyl shift that I can do? No, right? Because it has no methyl group. Can we do a hydride shift? No, because it already has 4 groups. So, if we can't do a methyl shift and we can't do a hydride shift, what must we do? Look at the longest path in the product. It has 1, 2, 3 carbons. And look at the paths on this bicyclo. It only has 1, 2 carbons. So deductively, what do you guys think is going to happen? We're going to have to break a bond, right? So, all right, which bond are we breaking? Think about it this way. What bond would be easiest to break? And I mean, here, since it's all symmetrical, it doesn't matter. But just to keep it simple and make it look most like our product, I'm going to break this bond between the bridgehead carbon and this carbon. So if I was to label this, let's say this was carbon number 1 and this was carbon number 2, I'm breaking this bond. I'm going to break this bond here. Okay? And once I break that bond, so I'm going to break this bond. I slice that open. And now I'm going to form that bond between 2 and whatever this carbon is. I forgot how many carbons we counted, but let's say if this was carbon 9. What is the original? How many carbons did we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that would be 9. Okay, so carbon number 9. I'm forming a bond between 2 and 9. Cool. Now, if you look, notice how many carbons our path is going to be. It's going to be 1, it's going to be 2, and it's going to be 3. So that gets us much closer to our final product. So let me draw that one more time. Okay, so that was carbon. Let me draw this one more time. This was originally carbon number 1. This was originally carbon number 2, 3, 4, 5, 6, 7, 8. So where am I now forming a positive charge? Where am I forming a positive charge, guys? If I broke the bond between 1 and 2, right, and I formed it between 2 and 9, which carbon no longer has 4 groups?
2.
No, carbon 2.
1.
Yes, because carbon 2, if you look here, carbon 2 has 2 implied hydrogens. If you look at our original structure, this has 2 implied hydrogens. One would be in the endo and the other in the axial preference. That still has its original 2 hydrogens. And like the other person just said, yes, because carbon number 1 didn't have any implied hydrogens. There's no hydrogens here. It only had those four groups, those four carbon groups. So carbon number 1 is going to be the one left with a positive charge. All right, cool. Now what happens? Look at our product and look at our intermediate. What's going to happen now? I need to somehow form an alkene here, right? So what's going to happen? How do I move that positive charge?
Is it hydride shift?
It is a hydride shift because 9, if you look at carbon number 9, originally it still had 2 hydrogens, right? It still had 2 hydrogens. And so it never lost those 2 hydrogens, right? I never lost these 2 hydrogens. But I can do a little hydride shift. This is a hydride shift to be able to move that positive charge. And here's the thing. I know that we're forming a secondary carbocation, but we're getting closer to our final product because that alkene is technically on carbons number 9 and number 2. Does everybody see that? We have to move that positive charge here at carbon number 9. So we do a hydride shift. Once we do a hydride shift, let me just redraw this one more time. Once we do this hydride shift, it's so ugly. So once we do that hydride shift, we place that positive charge on a carbon number 9. Okay, this was carbon number 9. Okay, cool. We're getting closer to our product. Maybe I should draw it up here. We're getting closer to our product. What's our, we're almost there. What's our final step? How do we make an alkene? We did lots of mechanisms on Friday on how to make alkenes. Remember, if I go back up, scroll back up to here, we made alkenes by depronating, remember? I also did another example, I think, over here. I did another mechanism, I feel like. Well, okay, but you know you can make an alkene basically by depronating. Here we depronated it with water and we formed an alkene here. We formed an alkene here by depronating one of these hydrogens. We could do the same process. We could do the same process here. So now where are we gonna, since we're forming that alkene between 9 and 2, we have to depronate where? Which hydrogen? Nine had 2 hydrogens, but we use one of those hydrogens to do a hydride shift. Now it only has 1 hydrogen. It only has 1 hydrogen, okay? And if you look at our product, there's 2 implied hydrogens. So there's 1 implied hydrogen here on 9, and there's 1 implied hydrogen here at number 2. But 2 already technically had those 2 hydrogens. Remember, I was showing you guys earlier, 2 still has those implied hydrogens. But now it has only 1 hydrogen because it formed an alkene. So we can say that because in our final product, 2 only has 1 hydrogen, we must have depronated that hydrogen, one of those hydrogens, with water. So we have water here, and it picks up one of those hydrogens. And the electrons between that carbon and that hydrogen are now going to be donated to make that alkene between 9 and 2. And so that is what forms this alkene, this double bond. Okay? So just to recap real quick, what did we do? We noticed that the alcohol, the hydroxyl group, was leaving. It left, okay? And we also formed an alkene. We formed an alkene here. So we counted our carbons and we made sure that there's no change in the carbon skeleton. And since we know that there's no change in the carbon skeleton, that's good. We may just have rearrangement. Since hydroxyl is leaving, we first pronated the hydroxyl group with hydronium because it's a good source of hydrogens or protons. This made water into a good leaving group. Once water left, we formed a primary carbocation at position number 9. That position number 9, because there wasn't any methyl or hydride shift available from carbon number 1, we knew that we had to break a bond. We broke that bond between 1 and 2. That bond between 1 and 2 was broken and it was reformed between 2 and 9. Since it was reformed between 2 and 9, carbon number 1 no longer had 3 groups. That formed a positive charge at carbon number 1. But the alkene is between carbon number 9 and carbon number 2. So what we did was a simple hydride shift with one of the hydrogens from carbon number 9 to give to carbon number 1. That placed a secondary carbocation at position number 9. Since we have a carbocation now at position number 9, we could simply depronate one of the hydrogens at carbon number 2, because in our final product, both 9 and 2 only have 1 hydrogen. So we depronate it with water to form that alkene between 9 and 2, and that gave us our final product. Okay? So we ran out of time, but I'm going to share this PDF. I want you guys to try C, D, A, and E. A and E, we already did several examples before. And do challenge question number 1131. And that's pretty much it. You'll finish chapter 14 tomorrow, and you will have a review session tomorrow with Eric. He'll finish the first half of chapter 14 pretty quickly. I don't know. He's just going to explain how to identify patterns in IR spectras. And then you'll just do a whole bunch of review with him. So bring questions, come prepared. If you have any more questions for me, please feel free to speak up. But besides that, I mean, I don't really have enough time to do these last 5 questions. So please feel free to either post it in the chat once you've tried these questions out, or watch the recording to see if you have a sufficient explanation for these last 2. And yeah, anybody else before I end the meeting and stop the recording? No? Okay. I'm going to stop recording.